Okay. Right. So should
ready?
Yeah, you go. Okay.
Yeah. Okay. So thanks everyone for joining. I will host today's session a little bit late notice, but it should be an exciting talk. We've actually got at least two of the authors here, but Qinghua is going to give the talk on optimistic natural policy gradients. And yeah, I think the floor is yours. If anyone has any questions, feel free to post them in the chat, or you can ask the question yourself, and I might also ask some questions. Otherwise, all yours, Qinghua.
Thank you, Tao, for the introduction. So yeah, it's really nice to come back to this seminar again and present another interesting research project by myself and Gellert, Andras, Shi, and Chaba. So today I will talk about optimistic natural policy gradient. So this is a very simple policy gradient algorithm that have several advantages compared to existing ones. So first, we will say this algorithm is purely on policy, which is similar to the practical policy optimization algorithms like PPO or TRPO. Second, we will see the sample efficiency of this new algorithm improve over the best existing ones by some dimension dependence. And third, we will try to argue this algorithm is the first computationally efficient one that can achieve optimal dimension dependence for linear MDP. And yeah, this work is a joint work with my wonderful collaborators. So Gellert, Andras, and Chaba, they are affiliated with Google DeepMind, and Chi is my PhD advisor at Princeton. Okay, so I will start with some folklore applications of reinforcement learning. So I think Google DeepMind used Monte Carlo tree search and reinforcement learning to develop the first superhuman AI agent that can beat human champions in the game of Go. And the robotic team in OpenAI, which no longer exists, I think. So they use reinforcement learning to develop a robotic arm that can play Rubik's Cube. And there have been also a lot of works that use reinforcement learning to play all kinds of video games like Atari, Dota, or StarCraft. And more recently, there has been huge interest in in fine-tuning large language models to better follow human instructions. Okay, so this picture is just a joke, so maybe I shouldn't use it because Chaba and Tor are working in Google DeepMind. So, okay, so I think so to some extent, the success of reinforcement learning, so these applications are largely attributed to huge computation power or extensive engineer efforts, and more importantly, novel and efficient algorithms. And the policy optimization algorithm is a class of algorithms that have been widely used in all kinds of applications. And I guess many of the audience here have used or heard about reinforce or proximal policy optimization, PPO, or trust region policy optimization, TRPO, or soft actor critique, SAC. And all these algorithms belong to the family of policy optimization. And in fact, if you want to solve some tasks with large action space or continuous action space, these algorithms, policy optimization ones, are the default choice for you to try. For example, like when you want to do robotic tasks, or you want to align your AI system with human interests. Okay, so these are all the background knowledge. And now I will tell you three motivations which motivates us to start this research project from the very beginning. So first, if you look at the policy optimization algorithms used in practice, you will see most of them are on policy. So by on policy, I mean we are using the data collected from the current policy to further improve the current policy. And many practical policy optimization algorithms roughly follow this three-step recipe. So first, we can execute the current policy to collect a bunch of trajectories. And then we construct some policy gradient estimator using this data collected in step one. And after that, we can perform policy gradient using the gradient estimator constructed in step two. And we repeat this process again and again until you get some high performance policy. Yeah, that's the typical recipe of practical policy optimization algorithms. And the reason they prefer to use on-policy data sampled from the current policy, is because in step two, when you construct this gradient estimator, we use the technique of importance reweighting. So that means if you use some data sampled from a policy that is very different from your current policy, the variance of your importance reweighting estimator will be super large. So that's why people prefer on-policy data in practice. However, if you look at IO theory, you will find most theoretical algorithms are off-policy, at least to my knowledge. So by off-policy, I mean they're using data collected from historical policies that could be very different from your current policy. They use all these data to evaluate your current policy and do some further improvement. Question?
Maybe this is super naive, but I guess if you sampled on policy from a deterministic policy, you might have very high variance of the gradients. Somehow this on policy sampling is only having small variance for randomized policies. And then you might wonder, like as they get closer and closer to deterministic, maybe this is a really bad idea. Any thoughts on that?
Oh, so you are saying, oh, I think whether the policy is, or whether the policy or transition.
Yeah, like if I, if I sample from a deterministic policy, how will I get an estimate of the gradients, unless maybe the environment is nice?
Okay, so if you are, suppose you are evaluating a deterministic policy, and you are sampling from this exact policy. So whether the policy is deterministic or not doesn't matter that much. You can still construct a very high quality policy gradient estimator. But if you are using data sampled from one deterministic policy to evaluate another deterministic policy, in that case, that would be super bad. Chava, do you have any comment? You're muted. You're
Maybe
muted.
just comment is that I think that it's coming a little bit later of how these gradient estimators are constructed, and it will be very clear that it's not about whether the policy is deterministic or not. It's the likelihood ratio helps you to go off policy a little bit. You could get away with on policy as well. The reason you want to bring in off policy is because you're hoping to make better use of all the samples that were produced previously. So to improve sample efficiency, you want to be there. And for that, yeah, you might want to give up on just using deterministic policies and then give up a little bit on performance to see whether you can gain something. But at this stage, probably it's kind of unclear whether this is even feasible or a good plan, right, Qinghua?
Yeah. So I think.
Yeah.
Is it true? If I'm in a bandit and I have a deterministic policy that plays always on one, how do I estimate the gradient of if I increase the probability of playing on two?
Oh, okay. So you will see in later slides, our policy is never deterministic. So I think if you do policy gradient starting from a deterministic policy, you can never, if you are using like you are using merely some style policy optimization algorithms, you can never make progress on those actions, which has no probability mass at the very beginning. So
yeah,
in our work, we will use.
Yeah, we have to clarify a few things here. So there is the gradient dynamics, and whether the gradient dynamics on its own is sufficient to get you all the way to optimality, even when you're accessing the exact gradients. And so as Thor's example shows, with bandits, that's not true. If you start with a deterministic policy, then the information that you're collecting, well, the gradient appropriately phrased, it's going to be just the value or like the estimated reward. And since you're not getting any information for any of the other actions, this is, yeah.
Yeah, I think in that case, your reward estimator will be super bad because
Okay, yeah, I take it back. Like you have to randomize overreactions to get gradient estimates. Yeah, without that, it's not going to work at all.
Yeah. Anyway, perhaps we can talk about variant stuff later, and we can move on.
Yeah,
to now.
sure. Yeah. Sure. Yeah. So yeah, let's continue. Yeah. So if we check all those theoretical algorithms, you will see most of them are off policy. So that means they're using trajectories sampled from some policies very different from your current one. And most of the time, this choice is due to the sake of technical proofs. For example, when you're analyzing tabular MDP, you want to do some pigeonhole summation, and when you analyze linear MDP, you need to use some elliptical potential argument. So to use these technical tools, somehow you have to use offline, off-policy data. So to summarize, the current situation is practitioners often use on-policy algorithms, while we theorists mostly study off-policy algorithms. And this creates some discrepancy between practice and theory, which motivates us to ask the following question. Can we show on-policy algorithms provably converge to near-optimal policies? And if the answer is yes, how fast? Can we do it in polynomial samples? Okay, so yeah, so I want to emphasize that I have no intention to claim on policy is better than off policy. I just want to understand whether the widely used on policy methods make any sense in theory. Question.
Maybe I'm misunderstanding this slide, but do we have a good understanding of like estimation of off-policy gradients or convergence of off-policy gradient?
Oh, so okay, so I want to clarify a little bit. This is in the online setting. So by on policy, off policy,
okay.
it's not offline IO.
Got it. Okay, thanks.
Okay. Okay, so this is the first motivation. And second, at the current stage, actually, we already know many, so reinforcement learning can solve many different settings. For example, in the very basic tabular MDP, we have UCB VI developed by Azar et al. In 2017, which achieves the minimax rate. And in linear MDP, we have the least square value iteration UCB designed by Chi and his collaborators. And for general function approximation, we have Bellman-Rank developed by Jiang et al. We also have recently we have the DEC developed by Foster et al. But if we restrict our attention to only policy optimization algorithms, we will see our theoretical understanding is actually quite limited. So for the tabular case, we have Shani et al., so which is a very nice work. But when we look at the linear MDP, which is slightly a more complicated setting than tabular MDP, we have very few works that study policy optimization in the online setting. And for example, we have Agarwal and et al. And Zenet et al. These two papers that study policy optimization for linear MDP. And if you read those papers, you will find the algorithm design therein is actually very complicated. And despite the highly involved algorithm design, the final sample complexity is actually not that good. So I think Agarwal has sample complexity poly D over epsilon to the 11, So D is the dimension and of the linear MDP, and epsilon is the final accuracy. And the net achieved sample complexity D cubic over epsilon cubic. So this motivates us to ask the second question: can we design a much simpler policy optimization algorithm with much sharper guarantees? And finally, let's take a look at the state-of-the-art result for learning linear MDP. So we have the square value iteration UCB, which achieves D cubic over epsilon square, and this algorithm is computationally efficient. And we also have the net also we have the algorithm from the net et al. And they achieve the minimax rate for learning linear MDP. And but their algorithm is not computationally efficient. At least at the current stage, we don't know whether their algorithm can be implemented efficiently. And more recently, we have many works that achieves sample complexity D square over epsilon square plus D to the fourth over epsilon, and their algorithm is also computationally efficient. However, if you look at all these results, you will see no algorithm can achieve the optimal D square dimension. There is no computationally efficient algorithm that can achieve the optimal dimension dependence D square. So we ask the third question: can we design computationally efficient algorithms with optimal dimension dependence D square? Okay, so these are all the motivations for our paper. Is there any question for this part? Okay, if not, we will look at the algorithm. But before we introduce the algorithm, first let me define some basic terminologies for reinforcement learning to make sure everyone is on the same page using the same notation. Okay, so we consider finite horizon episodic MDP. And this MDP is specified by 4 components. We have an action space of cardinality capital S, an action space of cardinality capital A. We have a set of transition distributions, which tells us conditioning our current state action, what's the distribution of your next state. We also have a reward function, which tells you if you are at state SA, what's the expected reward you are going to receive. And throughout this work, we will assume all transitions and the reward function, these functions are unknown. And the learner must learn a good policy by solely interacting with the MDP. And specifically, let me define how the learner interact with the MDP. So the learner interacts with the MDP in the form of episode. In each episode, the learner always starts from a fixed initial state, S1. And at each step, the learner first observes the current state, SH, and then takes action AH. After that, the learner will transition to the next state, SH plus 1. And this state is sampled from the transition distribution, conditioning on the current state action. And then the learner will receive a reward. And the current episode will terminate after the learner receives the reward in the final step. And then the learner can restart a new episode. And this is the interaction protocol. Is there any question about this part? Okay, great. And I want to further define several widely used notations in studying MDP. The first one is policy. So policy is a set of functions, and each function maps from the state space to the simplex over the action space. So intuitively, you can think of a policy as some guidance that tells you how to pick your action conditioning on your current state. And given a policy, pi, we can define its value. We define the v value of policy pi at the state s to be the expected cumulative reward you will receive if you start from state s and follow policy pi to pick your action. And we define the Q value of policy pi at state S and action A to be the cumulative reward you will receive, conditioning on your current state action being SA, and you pick your future actions according to policy pi. And we define the optimal value to be the highest value that can be achieved by any policy pi. And the goal of our work is to learn a near optimal policy pi such that its value is as close to the optimal value as possible. And the closeness is measured by this accuracy parameter, epsilon. Okay. So without making any structural assumptions, there's you can never do better than UCB VI. So basically, to learn an epsilon open policy, you will need at least this number of samples. So S is the number of states, A is the number of actions, and H is the length of each episode, and this epsilon is the accuracy parameter. However, in practice, we often tackle problems of exponentially large state space. That means this S can be prohibitively large. So if you have some theory that linearly scale with this S, that basically your theory means your theory is not that useful for real world applications. And why we have such linear dependence on the number of states? That's because in deriving this minimax race, we are treating each state as independent. We are not generalizing any knowledge across different states. This is in some sense similar to non-parametric estimation in supervised learning. So in non-parametric estimation, if you pose no assumption about the underlying hypothesis, you will suffer the curse of dimensionality. So basically, your sample efficiency will scale exponentially with the dimension. But real-world problems often have structures. For example, in supervised learning, many problems have linear structure. So we can use linear regression to solve those problems. And we don't need to suffer exponential dependence on the dimension. We only need our sample efficiency only scales polynomially with your dimension. And the counterpart of linear regression in reinforcement learning is called linear MDP. So what is linear MDP? It basically assumes you have a feature mapping phi, which can map your state action to a d-dimensional vector. And given this feature mapping, all your transitions and rewards can be written as a linear function of your feature mapping. And in the standard linear MDP setting, we will assume this feature mapping phi is given to the learner. And all those linear parameters in these linear functions are unknown to the learner. Is there any question about this part? Otherwise, I will talk about...
linear MDP can cover the tabular case, right?
Oh, yes. So you can parameterize tabular MDP as a linear MDP. In that case, your feature function will be from your state action space to RD, where D is equal to S times A.
Oh, I see. Okay.
So basically, you do one hot encoding.
Oh, got it. Thank you.
Question?
The normalization conditions here is sort of boundedness of all these features.
Oh, yes. So we assume your feature norm is always upper bounded by, say, square root of D. And this posi, the norm is always upper bounded by 1. And this theta is like always upper bounded by capital H or square root D of capital H.
And if you replace those bounds with something else, would you expect those to appear logarithmically in your regret bounds or polynomially, or what would be the change?
Okay, that's a great question. I expect some of them will appear polynomially in the bound.
Okay. So should we be worried that the bounds depend on the dimension?
If your I think so. So if you formulate the tabular MDP as a linear MDP, your feature norm will scale with square root d. In that case, it's like square root s times a. So your norm can scale with your dimension. Hopefully, it doesn't scale too crazily.
I see. So this square root d is a natural choice because of that reduction to the tabular case.
Yeah, I think it's motivated by the tabular reduction.
I see. Thanks.
Any other question? Okay, so let's move on to the algorithm. And before introducing our algorithm, I think it's better to first recall the classic natural policy gradient algorithm by Kakad et al. By Kakad in 2001. So this algorithm is actually very simple. So assume you know the ground truth translation function and you know the ground truth reward function. In each iteration, you first use this ground truth translation reward to compute the Q value for your current policy. And then you use the computed Q value to perform one-step soft policy iteration. And if you know mere descent, this is just doing one-step mere descent using the Q value, the negative Q value as your gradient. And importantly, this simple MPG algorithm is the prototype of many very important practical policy optimization methods. For example, you can view, in some sense, you can view PPO and TRPO as MPG plus some heuristic modifications plus some engineer magic. So, but if you want to apply MPG to our setting, there is some difficulty you need to address. So first, you don't know the model, you don't know the translation and the reward. So for in each iteration, you cannot exactly compute this value function for your current policy. So what we do here is we replace this exact Q value with some optimistic estimate. And crucially, this estimate is collected using data only sampled from the current policy. In other words, we are using on-policy data to estimate a Q value for the current policy, and then perform one-step mere descent using the estimated Q value. And the output policy of our algorithm is sampled uniformly at random from pi 1 to pi capital K. And this is the whole algorithm, optimistic MPG. So for those who have read Cai et al., I think you will notice this algorithm is actually very simple to the OPPO algorithm in that paper. So I want to remark the difference between these two works. So first, our algorithm is purely on policy. So that means we are using data only using data collected from the current policy. But Cai et al. Uses all the historical data. It turns out that this subtle difference in sampling strategy matters a lot in your proof. And as we will see later, our algorithm actually applies to linear MDPs. But the algorithm in Cai et al., it only applies to linear mixture MDPs due to some subtle technical challenge in the proof. Okay. And also, I want to remark that our algorithm can also be extended to handling linear MDPs. So please.
Linear mixture MDP, is that like more general or?
I think these are two different settings. So none of them is more general than the other.
Oh, I see.
Yeah.
Okay, thank you.
They can capture different problem settings. Yeah.
Okay.
Okay. So NK episodes in total, NKH interactions. Oh yeah, we will get to that point later. Oh yeah, you're right. So each episode contains H H samples or H transitions. Did I answer your question? Okay. Okay, so to apply this algorithm to different problems, we still need to specify this subroutine. How do we implement this optimistic policy evaluation? And yeah, so in the remaining talk, I will tell you how we implement this subroutine for tabular MDPs, linear MDPs, and what kind of guarantees we can get. And if time permits, I will also quickly go through a proof sketch for the linear setting. So, okay, let's as a warm up, let's first look at the simple tabular setting. So in this case, this subroutine is actually very simple. So given a dataset D and a policy pi, we first estimate the model transition and reward using this dataset D. We denote this estimated transition and reward as p hat and r hat. And then we pretend p hat, r hat are the true transition and reward. We use p hat and r hat to compute the value for policy pi. And in this process, to compensate for the estimation error in p hat and r hat, and also to encourage exploration, we will add some UCB bonus when computing the value. So mathematically, it's equivalent to these equations. So basically, you follow the Bellman equation under policy pi, and replace the ground truth transition and reward with the estimated transition and reward. And also in the meantime, you add some bonus BH. This is just standard bonus. Okay, so this JH is the number of times this SA pair has been visited in your dataset. So this BH measures how frequently you have visited SA in your dataset. And by choosing your batch size n, so recall this n is the number of samples you sample for each policy. By choosing this batch size to be SA over epsilon square, and by choosing the total number of iterations to be 1 over epsilon square, and by choosing your learning rate to be epsilon, you can show your output policy pi out is epsilon optimal with probability at least 1/2. And the total number of sample complexity is k times n, which is roughly SA over epsilon to the 4th. So I want to say that, so for cleaner presentation, I didn't include the dependence on the horizon length capital H, but you can check it in the paper. So all the dependents are polynomial. Okay, so this part I think is quite straightforward for most of the audience. Okay, now let's look at the linear setting. And this part is also pretty straightforward at the current stage. So if you know least square value iteration, you will see this subroutine is just using your collected data to perform least square policy evaluation. And because we are using samples, there is some estimation error. So we additionally add the elliptical potential bonus to compensate for the estimation error and to encourage exploration. So yeah, this is just least square value policy evaluation. Nothing fancy. So okay. Any question about this part? If you are not familiar with linear MDP, you feel free to ask questions about this part.
So here, the bonus, just about the bonus, it looks very different from the tabular case. So is it like generalization of the tabular case? How does it relate to that case? Yeah, frequency.
I think it's the same as the tabular case if you choose your feature vector to be one hot in coding.
Oh, okay.
Yeah, so because in that case, your covariance matrix will be a diagonal matrix, and your feature is a one hot vector. So you will get some square root 1 over counter.
Yeah, the diagonal matrix is going to count how many times you have seen a state action pair.
Oh. Yeah, it's not easy to think of such a bonus. Yeah.
Oh, I think it's similar to the bonus used in linear bandits,
Oh,
like linear UCB, those kind of stuff.
okay.
Or you can, or if you know the analysis of linear regression, you will see this bonus is very similar to the error bound in your linear regression.
Oh, I see. Thank you.
Okay. Okay. And yeah, so by choosing your batch size to be d squared over epsilon squared, your total number of iteration to be 1 over epsilon squared, and the learning rate to be epsilon, we can show your optimistic NPG can learn an epsilon optimal policy with probability at least 1/2. So the total sample complexity will be d squared over epsilon to the 4th. So obviously, this sample complexity doesn't look good in terms of the epsilon dependence. But however, it is the first computationally efficient algorithm that can achieve the optimal dimension dependence, d squared. And also, this algorithm is purely on-policy. So at least to my knowledge, this is the first on-policy algorithm that can converge to the optimal policy within polynomial samples. And now I will tell you, okay, so because this epsilon dependence, it looks very bad. I will show you how we can improve this dependence using a very simple trick. And this trick is, in some sense, is also very similar to what people are doing in practice in PPO or in TRPO. So recall in our algorithm, in each iteration, we collect some new data using the current policy, and then we perform one-step mirror descent according to this formula. So if we pick the learning rate to be not too large, to be small enough, we will see our policy is actually being updated very slowly. And formally, we can show that given policy pi m and pi n from 2 different iterations, the induced state action distribution of these 2 different policies can be very close if m minus n times your learning rate is small. That means sampling from this policy pi m is roughly the same as sampling from policy pi n if m and n are not too far away from each other. And in our algorithm, because we choose the learning rate to be epsilon, so as long as the m minus n is upper bounded by 1 over epsilon, these 2 policies will be very close. And as a result, we don't need to sample fresh data every 1 over epsilon iterations. We only need to sample it once and reuse it for the following 1 over epsilon iterations. And by doing so, we can improve the sample complexity for tabular MDP, for linear MDP, by a factor of 1 over epsilon. And specifically for linear MDP, we get sample complexity d squared over epsilon to the 3. So this improves question.
Just in the chat, there's a question from Ziyi Chen saying that this looks like extra gradient.
I think this is different from extra gradient, right? So in extra gradient, you can do in some sense you are performing gradient is 1 step ahead. So
Yeah, I also also seems different to me.
Yeah, this is just standard mirror descent.
Yeah, but somehow reusing the data here. Do you think there's hope to get the epsilon squared rate?
Okay, actually, I know how to get epsilon squared by using a very different approach. I can tell you at the end of the talk. So it's a rather different approach.
Awesome. Okay.
But that one is not. But we need to make some modification, which makes the algorithm a little bit ugly. So the current one looks very clean. So okay, so if we compare the sample capacity of our current sample capacity to the best previous ones, we will see our result improves the previous ones by a factor of dimension. So in terms of the dependence on epsilon, we are the same. Okay. Okay, now we have time for the proof. Okay, I will do the proof for the setting of linear MDP, and with no data reusing. Okay, so but the proof with data reusing is basically the same. So to start with, I want to first state the following lemma. So the following lemma says that with high probability, your value estimate in each iteration satisfies the Bellman equation under your current policy pi k with high probability in an optimistic way. So if you recall the Bellman equation under policy pi, we should have this part equal to this part. But now our estimate satisfies this relation in an optimistic way. So this part is larger than this part. However, the overshooting degree, the degree of over optimism, is upper bounded by your bonus. Oh, sorry, there should be a constant 2 here. Okay, this the proof of this lemma is relatively standard. It follows basically the same as the analysis in all those previous linear MDP works. Okay, and now with this lemma, we can easily analyze the suboptimality of our algorithm. So first, we want to we decompose the regret. This is not actually a regret because for each policy we executed more than once. So this is some cumulative suboptimality with our policies. So we decompose this cumulative suboptimality into 2 terms. So the first term measures the difference between your optimal value and your value estimate, and the second term measures your estimated value function and the true value function. And let's control these 2 terms one by one. For the first term, we can use the standard policy difference lemma to decompose it into 2 other terms. The first term can be, okay, so if you know policy difference lemma, this step is straightforward. And for the first term, we can easily control it by the regret of mere descent because we are running mere descent at each state using this QK, using this estimated value function as our gradient. So we can control this step by mere descent, the regret of mere descent. And for the second step, it measures the Bellman error under policy pi k. So according to lemma 1, this term, because our value estimate QK always satisfies this Bellman equation optimistically, so this error is always positive. So minus positive is negative. So you get this. So you can bound the first term by this quantity. And for the second term, we can easily show this term. We can reuse lemma 1 to show this term is upper bounded by your expected bonus. So very importantly, we should notice that this expectation is under policy pi k, and this bonus function bk is also computed using data sampled from pi k. So what does it mean? So if you use a lot of data sampled from pi k to compute the bonus, you should expect the expected bonus under this policy to be very small. For example, if you are playing multi-arm bandits and you keep playing one arm, then the bonus at that arm should be very small, right? So yeah, so by plugging this equation into here, we can bound the second term by this quantity, and putting all pieces together, we get the final regret. So if you have read any paper about linear MDP, you will see this proof is very straightforward. There's nothing fancy here. Okay, but it's quite surprising that a very simple algorithm and a very simple analysis can give you a much better result than previous works. Okay, so that's it for all the presentations. So if you have any question, yeah, feel free to ask. Or you,
Thanks for your nice speech. I just learned a lot. So I just have just a general knowledge question. I remember you have learned many papers like about a V-learning, right? Like that's a kind of value iteration. Usually, value iteration can be very sample efficient. Yeah, right. But so what's the advantage of policy optimization over like a value iteration?
oh, okay, great question. So in theory, if you only look at the sample efficiency, value iteration can already give you the minimax rate. I don't see a clear advantage. But in practice, I think people use policy optimization algorithms a lot, especially for those tasks with continuous action space or large action space. So I feel it is interesting for theorists to study what people are actually using in practice. Chava, do you have any comments?
You're muted,
No,
too.
just finish what you're saying and
Oh, okay, yeah. So I think, so in my own view, I think I feel it's intellectually interesting to study the algorithms that people actually use in practice, especially when they use some very different design from our theoretical algorithms. It would be nice for us to understand whether their different design can actually work in theory, or there is any failure case of their design. Maybe we can get some insights or inspirations from studying their paradigms. So that's my own understanding.
Thank you.
So Chaba,
yeah, it just a reflection on this difference between the value iteration and policy iteration, policy optimization, that these bounds seem to depend logarithmically on the number of actions. So that is promising from the perspective if you have a large action space, at least. How about the bounds that we have for value iteration type algorithms like LSVI, UCB, or whatever algorithm you are thinking about?
oh, right. They don't have, they don't depend on the number of actions. Yeah.
Okay.
Yeah,
so that seems to go contrary to.
But I guess if your action space is super large, there's no way you can implement UCB LSVI efficiently because you need to compute argmax. Is that true?
Oh, yes. Okay.
If you have a huge action space in terms of
Right.
I see. Got it. Thank you.
How different it is to implement an algorithm that needs to sample from a huge action space, from a Boltzmann distribution that basically expressed in a very similar way as the maximization problem?
I think, okay, so I don't know if we can implement this one efficiently if the action space is super large. Yeah, I agree. I'm just saying if the action space is too large, maybe all algorithms will be computationally inefficient.
I guess what people do in practice is that they just use another function approximator technique to represent the policies in such a way that by design, sampling actions from the policy is cheap. And if you did that, like you would introduce another, function approximator, then presumably you would, if you are able to control the errors of this, then both value iteration and this policy optimization things should go through. Like the bounds would not change much.
Actually, I'm curious, what do we have for linear bandits? Because I think we have similar computational issue for linear bandits. Do we have any efficient sampling strategy for linear bandits? Or
a lot of times people want to reduce it to linear optimization. So if you accept that as an answer, so if linear optimization can be done efficiently over your action set, then you say that
I see.
Like,
Yeah, makes sense.
I'm happy to rely on an oracle that solves
Mhm.
linear optimization over my action set.
Mhm.
Whether you accept that as a solution concept or not, that's a question. And I think that's what being questioned here, because effectively, this is also what you need to do here, right?
Right.
Maybe you should accept that. I mean, in a linear bandit, if you don't have efficient way of doing the argmax, there's no way to, even in the offline problem, efficiently find a near optimal action.
Yeah.
Right.
Yeah.
That's true.
And there you have convexity and everything, so the average action would satisfy that condition.
And so in RL, it seems we are a little bit further away from this, because if you start to add these bonuses, then you're destroying the linear structure unless you would play around with the bonuses, which people don't yet do.
Mhm.
Yeah.
Yeah, and I guess this algorithm is very naturally scaling with d squared computation as well, right? Calculating all these, or d cubed even, but calculating all these matrices and doing the bonuses and so on.
Yeah.
Whereas I guess I think of an algorithm like reinforce or something, like the most basic stuff would be linear in D.
Right. So cheap exploration in terms of dependence on D, computational complexity in D, it's, yeah. Even for linear bandits, it's,
I think for reinforce, at least in the regret bound. Oh wait, you are talking about reinforce. Okay. For reinforce, I have no idea whether it can work in the online setting or not.
Yeah, me neither. I guess it's just an observation about the compute. Often people are using these policy optimization algorithms, I guess, because they scale linearly in everything. And this one doesn't because it has the bonuses.
Yeah, I guess
Like,
in practice,
yeah.
no one use bonus. They just do random exploration or R&D, those kind of stuff. But in Monte Carlo tree search, I think people use bonus. I think the algorithm developed by Chaba and his co-authors is actually using in AlphaGo. So they are using that square root bonus.
Yeah, or some variant of it. Yeah.
that's cheap to compute. It's a tabular setting, right?
Yeah.
Yeah.
I am super fascinated about this 1/epsilon squared that you were mentioning about. Can you say a couple of words about how that works?
Okay, so I can tell you how to do it by using an ugly algorithm. So that's the only I know. So, and also this algorithm is based on my discussion with Teng Yang. So Teng Yang is a student of Nan. So I think you all know him, right? So it's based on my discussion with him. So okay. So basically, what we can do is you can maintain a. So we are no longer sticking with the on-policy scheme. We are doing some off-policy stuff. So what you can do is you can maintain some policy cover. So basically, in each iteration, you sample some data. You only sample one data, and after you get this one data, you check whether your cumulative covariance matrix has doubled or not. So basically, whether you have reached some new direction sufficiently often in the past several iterations. And if you find that your covariance matrix has doubled, you discard all your previous data and you resample one data from each of your previous policy. So basically, you maintain a policy cover. Each time your policy cover gets updated, you resample all the data once. So that means, because your policy cover will be updated at most d times. So in total, you will sample d times d square over epsilon square. So which gives you d cubic over epsilon square. So your dimension dependence is worse, but you can get optimal dependence, epsilon dependence. But I don't know how to do d square or epsilon square. I remember Chava told me you have some work that can. When we write this paper, when we wrote this paper, you told me you have some d square or epsilon square with the other people at DeepMind. I remember. Is that? I misunderstood you.
I don't know. I don't remember.
Maybe I misunderstood you.
Yeah.
Does anyone else have any questions?
Hi. My internet.
Oh, hi.
My internet cut out. Thank you for the great talk. I might have missed something kind of in the middle, and my question's about that. So if this is a bad question, I apologize.
No.
So it was on this slide actually. You said that when two policies are close by, the data sampled from them is going to look similar, and so we should go a while without sampling. So is the idea that you take your policy at time k, and then for the next, however many iterations, you basically use the same trajectories collected before, and then you do your mirror descent steps using that kind of outdated information?
Yeah, exactly. So, for example, we collect the data in the first iteration. Then we can use the data collected from the first iteration to evaluate pi 1, pi 2, pi 3, to pi 1 or epsilon. So we can basically reuse all those data for evaluating. Oh, yeah, go ahead.
Yeah, no, okay, perfect. So I understood a bit of the setup. What I didn't really get, and maybe you mentioned this, was how like the bonuses and these V's and Q's change after you change your policy, because presumably that stuff all has to change in order to make the mirror descent make sense.
So the bonus only depends on your data set. It does not depend on your policy. So
okay, so then the QK, as you go from K to K plus 1, could you tell me how that was computed?
Okay, sure. Yeah, let's go back here. Okay, so we compute this QK using least square policy evaluation. So you can think of this as some function approximation version of Bellman equation under policy pi.
Okay, I see. And you're using that fixed data set for the next however many steps.
Yes.
But does this mean your Q thing is the same for different policies? Is that the idea?
Oh, it's different. So if you look at the definition of V function, so we have action sampled from your current policy.
Perfect. Okay, gotcha. All right, yeah, thank you. That answers my question.
By the way, on this slide, I think it's a bit outrageous to use sigma h here rather than sigma h inverse. This covariance matrix gets bigger as you add more data. That's a bit strange. But it's just notation.
Oh, right. I see.
Oh.
Taylor expansion.
Any other questions?
You also, I just read your paper. You also have a subroutine 3, which is for general OPE. Yeah, general.
Oh yes. So you can also, so if you make some strong assumption about you can actually do nonlinear function approximation, but as long as you make some assumption about completeness and eluded dimension, those kind of stuff. So you can have some similar, style algorithms for general function approximation.
Okay.
but that algorithm is not computationally efficient, and also that part requires some assumptions, which may seem a little bit too strong at the current stage of IL theory, but I'm not sure. It all depends on your research tastes, I guess.
Okay, thank you.
Some people think irreal dimension is too strong. Yeah, I think.
Yes, I would agree. There seems like there's so many reinforcement learning papers, and yeah, the knowledge base is so large that I just only.
I think things are gonna get much better because nowadays many people turn to large language models, so we will have less and less people. So no worries.
It's a good time to get into the
Yeah.
field because it's slowing down.
Oh, well, I'm just curious to all of you, especially Qinghua and Chaba. Do you intend to like also to do some large language stuff?
Qinghua is
I don't
already
think. Oh wait, I'm only studying transformer. I don't study language related stuff. So I guess I will only play with some toy transformer and see if it has some certain properties that might affect your decision making nature. So I'm now studying large language model because I don't have the computational resources, and also I don't have the engineer toolkits. So I guess.
Okay.
But I'm thinking what I can do for it.
Yeah.
Is
I'm not sure.
how about your child?
Yeah.
makes sense. Yeah. I think that's a good strategy.
Yeah.
You can't ignore them.
Yes.
So I have a question about this online versus offline thing.
Yep. Okay.
If I were to force you to formally define the difference, what actually
great.
would it mean?
Yeah, I know someone is gonna ask this question, and actually, I don't have a rigorous definition because if you ask, Olive is online or offline, I don't know. So the Olive algorithm for solving low Bellman rank problems, is that online or offline?
Maybe online or offline or off policy. Like, are you asking about the online on
Oh
policy?
yeah, the on policy, off policy. Yeah, this.
Yeah, on policy, off policy. Do you think Olive is on policy or off policy?
I think on policy. I think all algorithms that like they have a policy, they play it in an episode, and then repeat, and you have a regret bound. I mean, it's just like it runs the policy, it gets some data, then it finds a new policy somehow, it gets some more data, and on and on and on. That seems on policy to me.
There is a very specific technical definition, which is maybe not super useful, but strictly speaking, the on policy algorithm is the one that uses the data generated by following a policy to improve that policy. So it's like lives in the moment. It doesn't like save data from previous policies and then try to use those. Discard the data, like it requires an algorithm that kind of switches policies. So if you change your policy in a very continuous fashion, then maybe all this doesn't make much sense. But if you're switching between policies, then you can say, okay, I just switched my policy. Now I need to discard all the data that I have so far. I generate new data with my policy. Okay, like, can I add a bonus, please? Can I add some explanation? I don't know, like, what does it mean to follow that policy? But okay, that's a little bit wishy-washy. You do this, you generate the data, and then use that data that was generated to come up with a new policy, with the hopes that you're improving the policy. So this would be the intended meaning for on policy, but I'm not sure whether this is a satisfactory answer, because the boundary is going to be very blurry if you start to mix and match things.
I guess that would make UCRL2 on policy, for example.
UCRL2 is building a model.
But it discards the data at the end of every episode. Follows the same
So
policy.
you're not supposed to use anything from previous data.
But you do here because you update or do a mirror descent update based on some previous Q values.
You can use summary of the previous policy, but like it can't be a model. Sorry. Yeah, it's
Because I think
the spirit is that you have some parameters that describe your policy. It shouldn't be something that's suitable for avoiding an arbitrary policy. It's like it shouldn't be a model. You have a really complex and ignorant representation of everything else that was happening previously.
yeah.
So it's like,
Yeah.
these, I don't know how useful these classifications are beyond, giving people some hint of what the heck is going on. So it's like they're not meant for precise mathematical discussions. They're mostly meant for one human telling the other human what they did, and the other human may understand it faster.
I
Possibly
guess
get confused more.
Is there anything? I mean, it sounds like what you were just saying has to do with like the memory that the policy is allowed to use of like the system before some parameter was updated.
Yeah,
And
but it's
so-
very much undefined.
yeah. I mean, it's like the kind of thing that if you formalize it, does that get used? But it seems like if it was like there's partial observability, this might suddenly become significant.
Why partial observability is suddenly making a difference?
Oh, like where suddenly you need to use memory in order to be optimal, and I don't know somehow.
Oh, that's not even that type of memory. The type of memory we're talking about is just like remembering more about the interactions.
Well, so I suppose what I mean by memory in this case is that you take like some summary statistic of recent system interactions that builds a parameter,
Uh-huh.
and then if that parameter is, it has to be somehow measurable with respect to that history that you're keeping track of. So that's what I mean by memory.
Yeah.
I don't know if I'm making sense, but if you're doing something on policy with this like forgetfulness of the past thing, then the parameter that you're constructing necessarily has to be measurable with respect to something more limited.
Sure. I just don't understand how partial observability came into the picture. I mean, like you can apply these things to partial observable systems. As long as your conditions are met, you're fine.
Oh, I guess
how
you
interesting
said
that is.
what's the point in making these distinctions? And I was wondering if like
Oh.
you have to say, oh well, like because we need memory in this partially observable system, then you have to use something off policy.
No, I think that people make this distinction because if you try to use past data generated from other policies to evaluate some new policy, then you have more issues to deal with than if you were just head-on policy. And also, if you go back to old literature in TD learning, some very nice things are happening to the update dynamics if you're on policy, which are not happening in off-policy case, which give people headaches. And so that distinction was very useful there to describe these troubles. Maybe it's less useful here when we're talking about how to design these efficient exploration algorithms. I think that's the historical reason we're talking about on policy and off policy. Teeter learning is not compatible with off policy data.
Okay. Very interesting discussion. Thanks a lot for the presentation.
Yeah.
Yeah, thanks a lot. Yeah.
All right, maybe I stopped the recording. Maybe I should have stopped the recording.